All right, estimating limits graphically. Let's talk about what a limit is first. When they are talking about the limit, they want to know what y is doing as x is doing something else. So when they say the limit as x approaches this, what they're saying is if you are going towards this c for x, whatever constant this is, let's say this is, 4, okay? They're saying, what is y doing as you move towards 4 with your x values from the left and the right? So if I go 0, 1, 2, 3, 4, 6, 5, 4, right? Like as I'm moving towards 4, what is my y doing? Well, it's going towards this number right here, whatever this number is, this L. So let's call this like 3. Okay, so as my x has moved towards this constant here, my y's are moving towards this constant here. That is your limit, okay? Now, we will talk about what actually happens at the point, the value at the point, but what the limit is asking you, it is saying, what is y moving towards as you get closer to x, this x value? What's happening with y? And that's what a limit is. And the first thing we're gonna do is we're just gonna look at graphs and say, what is my y doing when I look at this graph, all right? And so we're gonna move through this really quickly because we're gonna move to some algebraic ways to solve for limit, all right? So let's look at this first one. Estimate the limit. And so let's look at this terminology here. The limit, that's what this LIM stands for, as x approaches 2. That tells you what x value you know you want. And then this in parentheses is the function itself, the function they want the limit of. This is a linear function, right? Y equals mx plus b, negative 3x plus 1. It's a line, all right? So they've given us this line, and they want to know what my y is doing, all right? So we are moving from the left and from the right to this value 2. That's where we get it from, x equals 2. For my y value on the left-hand side and the right-hand side, the 2, and if I can highlight it here. So if I'm looking at this 2 value, right, that's the value I'm moving towards, then you can see that from this side, I'm moving towards 5. And from this side, I am moving towards 5. And so your limit here would be 5. That's what your y value is moving towards as you get to the 2 on the x-axis. All right, so your limit here would be 5. That would be what you would estimate it to be. You would say, well, this is, or negative 5 rather. This is moving towards that negative 5. And so my limit then, as x approaches negative 2, or x approaches 2 would be negative 5. My limit here would be negative 5. All right, and so it would actually be listed that way. Limit as x approaches 2 of this function equals negative 5. And that would be your limit. I mean, you literally look at the graph and you say, what's it moving towards? Now, this is when your function actually equals that number that it's moving towards. You can see that it's a linear function. There's no breaks, there's no holes, there's no asymptotes, right? It's a continuous function here. And so for a continuous function, your value at that point and what it's moving towards will be the same thing. All right, but look at the next example. Example 2, top 737. They want the limit as x approaches 3. They've told us right here, right? Limit as x approaches 3. And so 3, well, that's right here, okay? What do you notice on this graph at 3? What is happening at 3 on this graph? What's there?
6.
But technically, there's not a 6 there. What is there? There's a hole, okay? There's a hole in the graph. So, again, my limit then is what is it approaching? Well, it is approaching that 6, right? You can see that from the bottom of this graph and from the top of this graph, it is definitely moving towards 6. Now, when you get there, it is not 6. It is a hole. But the limit is what it's approaching, not what it's actually defined. So, again, you would say, well, based on this graph, the limit as x approaches 3 of x squared minus 9 over x minus 3 is definitely 6. I can see that. It's moving towards 6, even though when I get to 3, there's a hole in the graph. That's okay. My limit is not tied to what it's defined there if it's not a continuous function. All right? And so that's what this next concept tells us. If you look at the bottom of page 737, you see this breakdown of things that can happen with limits. All right? So let's look at the 3 scenarios that can happen with limits. The first thing that can happen to a function is it is undefined. There's literally nothing that works at that particular point. A good example is there's a 0 in the denominator, and you definitely cannot evaluate that graph at that point because it causes a problem in the graph. And so there are going to be times like this first one where that value at the point that you're trying to get to is actually undefined. There's a big hole or there's an asymptote, all right? And so you are just telling me what it's moving towards. The second thing is it is defined, so look at the middle one, but you can see that it jumps out of the function. So you definitely have a point at that constant x, but it is not what the graph is approaching. You can see here the graph is approaching this number here. So you can say the graph is actually approaching that green, right? Now when I get to C, the graph is actually way up here at this red part up there. But my limit would not be the red part. My limit would actually be the green, what it is approaching, okay? And then you have this third type. You have it approaching this number, and it's actually defined at that number. All the same thing. What it's approaching and how it's defined is exactly the same, okay? And that is also the limit. So when you think about limit, don't think about what the function actually equals at that point necessarily. You think about what it is approaching, all right? What is it actually approaching? All right, and then we get into some specifics, all right? We have what's called weighted limits here. Top of page 738. One-sided limits. So we look at a graph from the left and from the right, all right? When I say left and right, I mean physically, all right? So I mean the left-hand side, those are your negative numbers. The right-hand side are your positive numbers on a number line, okay? Right? So if I'm coming from this direction, I'm coming from the left side of that number, meaning whatever's less than it. And if I come from this direction, I'm coming from the right-hand side, which is what's bigger than it, okay? And so you can actually evaluate the left limit and the right limit because they can approach 2 different things sometimes. In order for you to have an overall limit, those have to be the same thing, all right? So when you look at limits, you can say, okay, from the left-hand side, I'm approaching this. From the right-hand side, I'm approaching this. Are they the same? If they're the same, then you have an overall limit. If they're not, then you just have a left and a right limit. You don't have an overall limit. You have 2 different ones. So look at these examples they've given us. The first one is obvious, right? Here we go. We have this function, and it is an absolute value function here with a rational, an absolute value rational function. From the left-hand side, so look at this notation here. This little guy with a negative, so we want it as it approaches 0. So we're definitely going towards 0 for my x's. But then you see this little tiny negative to the right side of that 0. That means from the left-hand side, literally from the negative, right? From what's less than 0. And you can see over here that from the left-hand side, right, I am approaching 2. Does everybody see that? So from the left-hand side, as I go towards 0, my y value there is going to be -2, right? Everybody see that? So my left value, my left limit, rather, the limit as x approaches 0 from the left-hand side of this function is going to be -2. All right, let's look at it from the right. And so if you look up here, my notation has a little plus sign. Well, that means from the right side of the graph of the number that I'm moving towards. In this case, I am moving towards 0 again, right? From the right-hand side. So now we're going this direction, right? Coming from the right to that number. This limit is something else. What is this particular limit? Yeah, it's +2. So I have a left-hand limit and I have a right-hand limit. But here's the problem. Now they're asking me for my overall limit. All right, so you see it's just as it approaches 0 and you do not have a plus or minus on the either side of it. And so for this one, I'm going to say, well, here's the problem. My overall limit does not exist. So you would say does not exist. It does not exist because these two are not equal. I have a left-hand limit, -2. I have a right-hand limit, +2. I do not have an overall limit because those do not equal. So therefore, I don't have an overall limit.
So if they're like both -2,
then your overall would be -2, which is the next example here. If you look at this guy, they want the left-hand limit. From the left, right, I'm approaching 4, right? You can see this is 4 here, okay? So from the left, I'm approaching 4. From the right side of -3, I'm also approaching 4. So that means my overall limit then would be 4. Okay? So this one has an overall limit because from the left-hand side, I'm moving towards my y value is 4. From the right-hand side, my y value is also moving towards 4. Even though it's not defined there, I have a hole there. Even though it's not defined there, my overall limit is still 4 because from the left and right, I'm going to do the same thing. Okay? So we will talk about infinite limits in the next section. But when they ask for a rational, if they want a rational number for a limit, and your graph does something like this, we're approaching 4. Well, 4 on the graph is right here. I have an asymptote of 4, right? If they're asking for a rational limit, while these approach the same thing, they both approach positive infinity, right? As far as a rational limit goes, it does not exist. This has an infinite limit. This limit is positive infinity, which sounds counterintuitive to the word limit, right? But the truth is they're both approaching positive infinity, which is perfectly fine unless they want a rational limit. If they want a rational number for a limit, infinity is not a rational number, right? For infinite limits, this would actually be an overall limit of infinity. That would be my limit because they're both moving in the same direction. They're both approaching positive infinity from the left and the right. You can have the same thing and not have an overall limit. For this one, jumped. For that one, what's the problem? They want me to approach what number? What number am I moving towards based on this limit? 0. Here is 0. Well, from the left-hand side, I have a limit of negative infinity. It's going that way, right? From the right-hand side, I have a limit of positive infinity. So I have a left limit and a right limit, but I do not have an overall limit here. The overall limit does not exist because they are moving two different directions here. I want to show you one other type that does not exist here. In this case, they want us to move towards 0, all right? And so on this graph, 0 is right here. This is called oscillating, all right? And this is not, I'm not talking about a smooth, pretty graph, right? Like we did with sine and cosine, right? Remember we graphed sine and cosine and it was a wave. I'm talking about true oscillating where it just pings back and forth like a ping pong ball, right? It's not approaching anything because it is literally bouncing back and forth, right? And so this is called oscillating behavior. If you think about an oscillating fan that, goes back and forth, right? This is oscillating behavior. And this does not have an overall limit. When they bounce back and forth like this, you don't have an overall limit. And so if you see a graph like this, no overall limit exists. In fact, you won't even be able to find a left and right limit here because of the behavior that it's doing, this particular graph. And so they give you that concept summary in the middle of page 740. Middle of page 740, we have this. Why would a limit not exist? All right. It approaches a different value from the left and right. It increases or decreases without bound from the left or right. Or it oscillates in between two numbers. So it pings back and forth. Cannot oscillate. All right. So the last thing we're going to talk about in this section before we start doing the algebraic ones are limits of infinity. All right. What happens as your x approaches infinity? So specifically your x here is approaching infinity. We're not talking about an infinite limit on the y side of it, right? We're talking about as x goes towards infinity. So let's look at these. We're going to look at it without the graph first. Okay? We're just going to think about it algebraically without the graph. I have the function 1 over x, right? And I am making x go towards infinity. Infinity. All right, so if I were to just think about what's happening here, let's say we start at, I don't know, 10. All right, we're going towards infinity. So let's say it goes to 100. And then let's say it goes to 1,000. And let's say it goes to 10,000. We're still not there, right? We're going towards infinity. Are these numbers overall getting smaller or larger? 1/10. 1/10 compared to 1/10,000? Yeah, they're getting smaller. It is moving closer and closer and closer to what number do you think? They're getting smaller and smaller and smaller.
Negative infinity?
Not negative infinity. It will never get negative because these numbers will always be positive. But it is getting smaller and smaller.
0?
It's moving towards 0. So let's look at the graph. Yeah. So as x approaches positive infinity, right, which is this direction, right, my y value is continually getting smaller. It's never actually going to hit 0, and it's never actually going to be negative. But it's going to get infinitely close to 0. And so in this case, my overall limit here would be 0. That would be my limit. Because my denominator is getting continuously larger, and it's moving towards 0 here. Let's look at this next one. This one's a little bit different. So we're actually going to look at this in two pieces. We're going to look at the first piece, all right? This guy right here, negative 3 over x squared. Is my negative 3 changing? It stays a negative 3. What's happening to my denominator, though? Even with negative infinity, what's happening? You're squaring negative infinity. It's huge numbers. So what's happening? We just decided if the numerator is staying the same and the denominator is getting infinitely larger, what is this part moving towards? We just did it on the A. 0. Is my 2 changing as my x changes? Is there an x with my 2? No, so my 2 is not changing. So we have 0 plus 2. That's what it's moving towards. So my overall limit here would be what? 2. And you can see from this graph that as it approaches negative infinity, you have this horizontal asymptote here at 2. At 2. All right. And if I were to actually do this algebraically, just really quickly, if I were to get a common denominator here between these two pieces, what would it be? What's my denominator? Get a common
6.
denominator. A common denominator between these denominators.
Oh.
It's x squared, right? So plus 2x squared over x squared, right? So I could write that negative 3 plus 2x squared over x squared, right? Remember in bell work, my horizontal asymptotes, right? If it has the same, you use the coefficients. What are my coefficients there? 2 and 1. And that's not a coefficient. So this is approaching 2. I have a horizontal asymptote at 2, so it makes sense that it's approaching 2.
Okay.
All right. What would this be approaching? It's approaching infinity. It's taken to the 4th power in the denominator. What is this first part approaching? So 1 over a huge number, 0 minus 3. So what's my overall limit? Negative 3. That's what we're doing here.
Okay.
Okay?